Well, hello, this video is meant to be a full overview of SnapMirror in NetApp ONTAP environments. It's about 20 minutes, but I split it up in chapters. Now please look at the description where you can simply pick the topic of your choice if you like. And these topics are an intro to what SnapMirror actually is, synchronous versus asynchronous SnapMirror, replication types, some scenarios, snapshots, what are they and why are they needed in SnapMirror. We'll check out policy types and then we move on to SVMDR, SnapMirror Synchronous, LoadShare Mirrors and transition data protection. And finally we'll have a quick look at Snapmirror Active-sync and MetroCluster. The last one of which actually is not a SnapMirror solution, but still it's an important player in data protection and availability. And the terms RPO and RTO you may be familiar with, but I use them to close off and make some comparisons with what we have discussed. Now, what is SnapMirror? SnapMirror is a NetApp tool to protect data that lives in flexible volumes in NetApp ONTAP clusters. The basic idea is that data from a source volume will be replicated to a destination volume. This replication is done based upon a relationship between a source and a destination. And there are two major forms of SnapMirror. SnapMirror relationships can be synchronous or asynchronous. In a synchronous relationship, the data needs to be at the destination site before the client can be acknowledged that the data is safe. So the data will be in sync for 100%. In fact, the client will only be acknowledged that the data has been well received after it has arrived at the source as well as at the destination. So this means that there is zero data loss if the source would fail. All data will be on the target or the destination as well. In an asynchronous relationship, the data only needs to be at the source site before it will be acknowledged. It will be replicated to the destination site based upon a schedule, or manually. As a result of that, when the source volume fails, data that has not been replicated since the last successful update is lost. So where SnapMirror Synchronous guarantees zero data loss, SnapMirror Asynchronous cannot guarantee zero data loss by design. Now, if zero data loss is such a key feature, why don't we all use synchronous replication? I mean, why use asynchronous replication if there is also the synchronous variant, since we don't want to lose any data? Well, to start with, SnapMirror Synchronous has one major requirement. The latency of the relationship should be less than 10 milliseconds. If the latency would, for example, be 300 milliseconds, then the performance would drop to an unacceptable level. And next to the latency requirement, there are quite a few unsupported features. So if you do want to use SnapMirror Synchronous, the first thing you should do is have a look at the limitations, because they might be a reason to opt for asynchronous replication. Now, this is an incomplete list of unsupported features, like Snap Restore, SnapCenter, SnapLock volumes, FlexCache volumes, consistency groups, but as I said, there are quite a few more limitations, and the full list can be found in the description. Now, SnapMirror knows two different replication engines for every relationship, and these are DP or data protection and XDP or extra data protection. They represent a different replication technique. I think it will suffice to say that the DP engine is block-based and that it simply replicates physical blocks, where XDP also replicates blocks, but takes a more file system based approach where it tracks data logically based upon the file system structure. And since ONTAP 9.4, XDP is the default type that's being used. Even if you create a relationship and say the type should be DP, it will simply change it to XDP. A big advantage of XDP is that it's version flexible, so it supports different ONTAP versions on source and destination. And also it has a better performance than DP. So let's just say that the default and preferred version of SnapMirror is the XDP replication version. By the way, to be honest, there are two other types, and those are LS or LoadShare Mirrors and TDP, which is transition data protection. But they serve a completely different purpose, so we'll look at them later. Now let's have a look at some basic relationship possibilities. We can SnapMirror a source volume to a destination volume in the same storage virtual machine. We can SnapMirror a source volume in an SVM to a destination volume in a different SVM. And we can SnapMirror a source volume in a storage virtual machine in one cluster to a destination volume in a different storage virtual machine in a different cluster. Now, it's not very common to SnapMirror within the same cluster. Usually you SnapMirror between two data centers, and you either create backups from one data center to the other, or you failover from one data center to the other. But anyway, some additional preparations have to be made for SnapMirroring to volumes in different storage virtual machines or different clusters. First of all, if you want to SnapMirror between two storage virtual machines, the SVMs will have to be peered, whether they live in the same cluster or in different clusters. Peering simply means that you build a trust relationship between the two storage virtual machines. And when the SVMs are peered, replication can be bidirectional, so both storage virtual machines can contain source volumes as well as destination volumes. And obviously, if the storage virtual machines live in different clusters, you will first have to peer the clusters. Clusters also have to be peered. Transitive peering is not supported, so every cluster that needs a peering relationship with any other cluster will need to be peered directly. So in this example, cluster 1 has a peering relationship with cluster 2, but not with cluster 3, where cluster 2 has two peering relations. And to peer clusters, you first need to configure IP connections between the two clusters that you want to peer. This is done via the inter-cluster network. I know this is confusing because you will be familiar with HA interconnect between the two nodes in a single HA pair and the cluster interconnect between all HA pairs in a single cluster. But that is intra-cluster. The inter-cluster network is between clusters. So before you can start setting up SnapMirror relations between the two data centers or even between two clusters in the same data center, you will have to set up this inter-cluster network. Every node in every cluster needs a minimum of one LIF with the default intercluster policy for SnapMirror. And also, every intercluster LIF of every node should be able to reach every other intercluster LIF of every other node. This is like a full mesh setup, so that if any of the nodes fails, the cluster network is still guaranteed. Now, before we dig into SnapMirror relationship types, let's quickly look at snapshots. Snapshots are at the heart of asynchronous SnapMirror relations. I'm pretty convinced you're familiar with them, but just to make sure, a snapshot is a point-in-time copy of the active file system of the volume. Every flexible volume will have a starting point which is called the root inode. From this root inode there will be a hierarchy of metadata blocks that are interconnected by pointers, ultimately leading to the data block that contains the client data. For ease of discussion, I have left out all of the in-between blocks and pointers because for the purpose of this overview, we're only interested in the root inode and the data block. Now, a snapshot is nothing more than a read-only copy of the root inode. So when you create a snapshot, the root inode of the volume is copied to the snapshot directory in the same volume. And when the active file system receives new data or existing data is modified by the client, the data will always be written to new blocks, so the snapshotted blocks will never be modified or freed until the snapshot is deleted. And in asynchronous relationships, when you initialize a SnapMirror relationship after having created it, of course, a snapshot will be created at the source and all blocks that are in that snapshot will be replicated to the destination. This is called the baseline transfer. And after the baseline transfer is complete, both volumes will have the same snapshot. So they will now have a common snapshot. The updates will be incremental based upon the changed blocks in every new snapshot versus the previous snapshot. When you schedule the updates or do it manually, it doesn't matter. It will always create a new snapshot to replicate the changes. Now, we had a look at synchronous versus asynchronous replication and DP versus XDP as the replication engines. Now let's start with the asynchronous type, and let's imagine you want to set up a relationship where the changed blocks from the source need to be replicated to the destination on an hourly basis. And also you will not need to keep multiple backup copies on the destination volume, so all you want to be able to do is to failover from the source site to the destination site when the source site fails. Now there's a policy type called async mirror, which will do just that. So every time an update takes place, either manually or scheduled, all changed blocks from the source will be replicated to the destination, so after the update is finished, the source and destination will be identical again. So this is an asynchronous mirror with the async mirror policy. You will agree that this is not a backup, because both the source and the destination will have the same data after every update, except of course for the new data that enters the source volume during and after the update. So when you set up the SnapMirror relationship, either with DP or XDP, you can attach the async mirror policy to mirror your data from the source to the destination. Another policy type is the vault type. This is for backup and archive purposes. This means that the destination can be retaining multiple snapshots as backup. This type is only supported with SnapMirror XDP and not with DP. Also, this means that you cannot fail over to the destination. In this example, you see that the keep parameter is 2, and this obviously could be much higher depending on the number of backup snapshots you want to keep. There's a lot more to be said about this vault policy, but since this is a high-level overview, the details will be discussed in another video. And the third and very popular policy is the mirror vault type. This gives you the best of both worlds. It will allow you to fail over to the destination, and it can at the same time retain multiple snapshots at the destination volume. This type is also only supported with Snapmirror XDP. Now, how does this failover work and how to initiate one? At failover time, the destination volume becomes writable. It's of great importance that when you decide to fail over, you must be absolutely sure that the source is no longer accessible by clients. The failover itself does not do that for you because it's always initiated from the destination cluster. So you as an administrator are responsible for the complete fencing of the source. Obviously, clients writing to the original source and original destination at the same time is not a very good idea, to say the least. To fail over, you first need to QoS the relationship, which means that no new transfers will be started. After you have QoSed, you can run the Snapmirror break command from the destination cluster. Right after that, the destination will be writable, and when the original source comes back up again, you can reverse the relationship. Now, another very beautiful solution is SVMDR, or Storage Virtual Machine Disaster Recovery. This means that instead of replicating single volumes, you can set up an asynchronous relationship between two SVMs, where the source SVM will be a regular data SVM like any other, but the destination SVM is of the subtype DP-destination, and of course the SVMs need to be peered. Now, the baseline transfer will create new volumes on the destination SVM, and when an update is scheduled, all destination volumes will be updated, and new volumes will be created when the source SVM has new volumes. And destination volumes will be removed when volumes from the source SVM have been removed. And the failover will have the exact same result as the volume-to-volume relationship. Again, this is just an overview, but very quickly, you can use a parameter which is called identity preserve, which will not only replicate the data of the volumes, but also the volume settings and connected policies and things. Even the IP address can be replicated if you like. Also, you can unprotect particular volumes on the source which are not supposed to be replicated. And up till now we've seen some examples of asynchronous replication, but how does synchronous replication work? As discussed, data is written to the source and is written to the destination in parallel, and the client will only get word that the data is safe after both sides have the data. It comes with two policy types, sync and strict sync. With the sync policy, if the destination fails or is unavailable because of a network outage, the source will allow I/O from the client. So this is like a synchronous relationship with regards to reads and writes to the source. But of course, since the destination does not receive the data, there is no more zero data loss. If you demand zero data loss, you should use the strict sync policy. This policy will block all I/O to the source if the destination is unreachable. So with the strict sync policy, you will not allow new data to the source if it cannot be sent to the destination. And in both cases, when the destination becomes reachable again, the relationship will automatically be syncing again. So the takeaway is that with synchronous SnapMirror, the replication is not done on the basis of snapshots, because the data is written in parallel. There are some snapshots, however, but they are only there to make the resync faster after the destination was gone for a while, but now is back. And these snapshots are created every 6 hours by default. But this is adjustable, so you can have a common snapshot created anywhere between 30 minutes and 24 hours. Now, another relationship type is LoadShare Mirrors, which are of a very special kind and are currently only advised in clusters with multiple HA pairs. In a LoadShare relationship, the root volume of a storage virtual machine is replicated to a volume or multiple volumes in other aggregates of other HA pairs. So you could have a root volume of a single SVM to have many destination volumes if you have many HA pairs. The argument for running LoadShare mirrors of the root volume is twofold. It balances the read requests to root volumes of the storage virtual machine. So the root volume of the SVM will only be used to create junction paths, and clients will not read from it anymore. They will just read from the destination root volumes. so that will balance the load of read requests across multiple HA pairs. The second argument is that if you lose the HA pair that runs the root volume of a particular storage virtual machine, you will still have access to all NAS volumes in the other HA pairs because they have the read-only copy of the disappeared root volume. And then you can promote any of the remaining destination volumes to become the new source root volume. And it will automatically take over the relationships with the remaining destination volumes. Needless to say that LoadShare mirrors always reside within the same storage virtual machine. And then there's transition data protection. This is a type that becomes increasingly rare because it's only used to replicate data from a 7-mode environment, which was the ONTAP version before the clustered ONTAP version was released, and that was a long time ago. It comes with a separate tool that will help you to set up a relationship between a 7-mode environment and an ONTAP cluster. And after the data has been replicated, you could delete the relationship. But as I said, 7-mode is a legacy release, so the tool is needed less and less. Well, definitely hot is the Active-sync solution. Active-sync is an advanced and somewhat more complex solution based upon Snapmirror Active-sync. It is completely SAN oriented, so I2C and Fibre Channel are supported. We still have a source site and a destination site, but now there's a third site which runs a virtual machine that functions as a mediator, which kind of creates a triangle of communications together with the two sites. The mediator is not really a tiebreaker, although that is effectively the function it provides. It doesn't take any actions, instead it provides an alternate communication channel for cluster-to-cluster communication, and also provides for the automated failover if that's needed. The LUNs that are mapped to the clients with applications are part of a consistency group or of multiple consistency groups, so that all LUNs will be snapshotted in a crash-consistent fashion. So the applications will have zero data loss, and also failover is fully automatic and transparent to the application. This is referred to as TAF, or Transparent Application Failover, and it's a relatively new solution. It used to be called SnapMirror Business Continuity, but now it's called SnapMirror Active-sync. Now the final solution we need to have a look at is MetroCluster, and like SnapMirror Active-sync, MetroCluster is also a zero data loss solution, in that all data will be 100% in sync on two different sites. The big difference is that MetroCluster is not a SnapMirror solution. The software that's used to synchronize the data between the two sites is called Sync-mirror. So it's not SnapMirror but Sync-mirror. The basic idea of MetroCluster is that the aggregates are split up in two plexes. Normally an aggregate only has one plex, which is called plex 0. But in MetroCluster the aggregate will have two plexes, plex 0 and plex 1, one on each site. This is a physical separation. So you could say that a single aggregate is stretched over two sites, and both sites can be active, having their own stretched aggregates to manage. Let's say on site 1 you create a storage virtual machine, then MetroCluster will create a similar SVM on site 2, but this second SVM will not run until a failover takes place and site 2 will manage that SVM. MetroCluster is a very complex setup, which comes in two versions. The older version is MetroCluster over Fibre Channel, which can span a distance of 300 kilometers, and the newer version, which uses an IP network, so MetroCluster over IP, can span 700 kilometers. But as I said, it is a pretty complex solution, which is beyond the scope of this overview. MetroCluster deserves a separate full overview. And finally, let's have a quick look at two terms that haven't been discussed yet. Usually discussions on SnapMirror always start with these tools, but I deliberately put them at the end so that we know what we're referring to. So this concerns RPO and RTO. These are not NetApp terms exclusively, but commonly used in service level agreements. Recovery Point Objective, or RPO, is the maximum amount of data an organization can tolerate losing. RPO is calculated backward in time, so if your RPO is 1 single hour, the age of the files that you have after recovering from a disaster should be no more than 1 hour old. The RPO determines the frequency of backing up your data. And Recovery Time Objective, or RTO, is the goal an organization sets for the maximum length of time it should take to restore normal operations after a disaster. And an RPO of 0 in ONTAP environments can be achieved with SnapMirror Sync, MetroCluster and SnapMirror Active-sync, as we have discussed. RTO of 0 is currently not possible with ONTAP. Having said that, MetroCluster and Snapmirror Active-sync have a near zero RTO, so failover will be very fast. In MetroCluster, for example, the failover time is around 120 seconds or less, and with Active-sync it's transparent to the clients, so transparent application failover, but it's not really zero. Now in all of this SnapMirror stuff you may have missed SnapMirror S3, so that will be the next one.